Okay, in this last video about work, we're going to talk about the work that's done by a force when it's changing as a function of time or position. And so you can imagine that you have some particle trajectory, some path that the particle travels through, and at each point, the force that acts on it is just slightly different. And it's sort of continuously changing, like this. And you might be interested in what is the kinetic energy change of this particle as it goes through this trajectory. And so you know that the kinetic energy change is going to be equal to the work that's done by the surroundings. But the force changes all the time. And so how do we calculate that work when all we know is that the work done by a force F is F times the displacement? You have to have some sort of macroscopic displacement. So a way to get an estimate of that is to cut this section up into different chunks and to think about each of these as its own little displacement and to treat the forces that you know as average forces. So we can add up the work that's done through displacement 1, which would be F1 dot delta R1. We can add to that the work that's done through displacement 2, which would be F2 dot delta R2. And we can add to that the work that's done by F3 through delta R3, and so forth. So you can continue playing that game. Now what this gets you is the total work that's done, but it's an estimate. Because as the force changes, you're sort of saying this force, F1 or F2 and so forth, applies throughout this displacement. But it could be changing the whole time. So a better way of doing it is to cut it up into smaller and smaller chunks. So we might split this in half, and 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 we'll get more terms here. We could split them in half again, and we'll get more terms. As we keep splitting this further and further down, what we're going to find is that we're taking the displacement in each situation to an infinitesimal limit. That is, this displacement, this delta r, becomes dr. And so what you're actually doing is changing the sum to an integral from the initial location to the final location over the entire path. Now this is kind of a complicated idea and thinking about it in 3 dimensions, but you could imagine doing this in just 1 dimension. So we'll do a quick example. Let's say you have some force, Fx, that only depends on x squared, the displacement squared. And you want to look at how that force acts in going from location x1 to location x2. You have some force which changes as a function of the displacement. So we can calculate the work that's done in that case using this more continuous description, if you will, not a more continuous description, but a continuous description. So the work that's done in that case is the integral from x1 to x2 fx dx. We're only going in 1 dimension. And so we will go ahead and plug that in, and we'll say we're going to integrate from x1 to x2 bx squared, that's the force, times dx. What we'll get is x cubed over 3 evaluated at the endpoints. So that's b over 3 x2 cubed minus x1 cubed. Because the force is in the direction of the displacement and x2 is larger than x1, this work is positive. And so you can see that it still obeys this idea that the kinetic energy is greater than 0, or change in kinetic energy is positive when the work is positive. So that's just a really simple sort of abstract idea of how to do this kind of integration, but it's the level at which we're going to expect you to be able to do. Just these very sort of these polynomial descriptions of the forces, we want you to be able to integrate those. We're not going to ask you to do complete path integrals in 3 dimensions.